You ever look at a really tough problem and just think, there's gotta be a smarter way to do this, right? A shortcut? Well, in machine learning, that's kind of the name of the game. We're always on the hunt for those clever, elegant shortcuts. And today, we're gonna look at one of the absolute best, a method that takes a super simple idea and uses it to crack some incredibly tough patterns. So let's dive in and see how a tiny ripple can solve a huge puzzle. So take a look at this curve. It's a mess, right? It's complex. It's definitely not a straight line. How in the world would you even start writing a program that could trace a shape like that? This is exactly the kind of challenge machine learning was built for, but a lot of the usual ways to do it can be pretty slow and complicated.
But what if I told you the secret to cracking this thing isn't some massive, convoluted algorithm? Nope, it's an idea we can all picture right now. A single, simple ripple in a pond. If you can understand that one concept, you've got the key to the whole solution.
Okay, so let's put a formal name on our challenge here. What we're trying to do is called function approximation. We want to train a machine to see the hidden pattern in a bunch of data points, so it can make really good guesses about any new input it's never seen before. And to pull this off, we first have to get really comfortable with our one and only building block, the ripple. Now, in the machine learning world, this simple idea has a fancier name. It's called a radial basis function, or just RBF for short.
So what exactly is an RBF? Well, it's just what it sounds like. It's a function where the value you get depends on only one thing, how far you are from its center. That's it. It's exactly like a ripple in a pond. Its effect is strongest right in the middle, and it just kind of fades away the further out you go.
And here's how we actually write that simple idea down with some math. This is the most popular RBF out there, the Gaussian function. Now, don't get scared off by the symbols. I promise it's simple. See the x? That's just our input, whatever point we're looking at. And c? That's the center of our ripple. So that part, all x minus c, that's literally just the distance from our point to the center. Easy. And that little beta symbol, beta, think of that as our tuning knob. It lets us control the spread of the ripple. You know, do we want a wide, gentle wave or a sharp, narrow one?
So yeah, a single ripple is pretty basic. But here's where the magic really happens. We start combining them by strategically placing a whole bunch of these ripples across our problem, and then adding up all their effects, we can build a network that's powerful enough to trace out that crazy complex curve we started with.
And the structure is just beautiful in its simplicity. An RBF network has 3 layers. First, the input layer. That just grabs our data. Then, the hidden layer. This is where all our ripples live. Each little neuron in here is an RBF, and all it does is shout out how active it is based on how close the input is to its personal center. And finally, the output layer just listens to all those shouts and adds them up, each with its own little volume knob or weight to get the final answer.
And this simple setup leads to something pretty profound. RBF networks are known as universal function approximators. That's a fancy way of saying that, in theory, if you have enough of these ripple neurons in that hidden layer, you can mimic any continuous function you can dream of, to whatever accuracy you need. I mean, that is an incredibly powerful guarantee.
But being powerful is only half the story. The real reason RBF networks are such an amazing shortcut is how they learn. Their training process is shockingly fast, and it all comes down to this clever two-step trick that just completely sidesteps the slow, grinding methods that a lot of other networks have to use.
I mean, the difference is just night and day. A lot of traditional networks use this slow, iterative process, making tiny little adjustments over and over and over again. It's called gradient descent. It's complex, and it can take forever. RBF networks, they don't do that. They use a direct, two-step approach that is just dramatically faster.
And here is that two-step process. First, an unsupervised step. We just figure out where to drop our ripples in the pond. We could use a clustering algorithm to find the best spots, or honestly, we could even just grab some of our data points at random and use those. Then, step 2, the supervised part. This is the killer move. We use a single, direct math calculation to find the exact weights we need to combine those ripples to perfectly fit our data. One shot, no slow iteration. It's brilliant.
All right, that's enough theory. Talk is cheap, right? Let's prove just how simple and powerful this thing is by actually building one. We're going to walk through some code and build an RBF network from scratch to solve that exact problem from the beginning.
First things first, the setup. We're going to generate our target sine wave. That's the complex curve we want to learn. Then we'll create our hidden layer. We'll just choose 10 centers for our ripples and space them out nice and evenly across our input range from -1 to 1.
And here's the tiny bit of code to do it.
That first line, that just creates the wavy line we're trying to copy. And the second line, it uses a super simple function to instantly create our 10 ripple centers. Just like that, our stage is set.
Okay, next step. We need to build what's called the activation matrix. We'll call it G. A good way to think about it is like a sensor grid in our pond. For every single point on our wavy line, this grid is going to measure how high the water is at the location of each of our 10 ripple centers.
And we build this matrix with a really simple loop. All it's doing is going through every point on our target curve and asking each of our 10 ripple centers, hey, how close am I to you? It then jots down all those answers in our grid, which gives us a perfect map of our hidden layer's response to the data.
And now, the main event, the shortcut itself. This is step 2 of our training process. Now that we have that activation matrix G all filled out, we can solve for the perfect weights, we'll call them W, in one single lightning-fast calculation. This is where all the magic happens.
And here it is, this one line of code. This is the whole magic trick right here. That pin function, it's a seriously powerful tool from linear algebra that basically works backward for us. It looks at all the ripple activations we just calculated, it looks at the target curve we're trying to hit, and bam, it instantly solves for the perfect weight, the exact strength that each and every ripple needs to have. There's no slow grinding gradient descent, no endless iterations, just one clean, direct, and incredibly fast solution. Done.
And would you look at that success? The orange line is our RBF network's prediction, and the blue line is the true function we were trying to learn. I mean, look at that fit. It's practically perfect. And we did it with a method that's both super intuitive and computationally ridiculously fast.
So, what are the big things to remember here? First, RBF networks are universal approximators. They are powerful enough to learn pretty much any continuous pattern you can throw at them. Second, their secret weapon is that fast two-step training. That trick of placing the ripples and then just solving for the weights is a massive shortcut. And finally, the whole thing works because of their local responses. Instead of one giant, complex brain trying to solve everything, you have a team of simple little experts where each one just masters its own tiny neighborhood. It's just so efficient.
Which kind of leaves us with a final question to chew on. We just saw how combining a team of simple, local experts, our ripples, can solve a really complex global problem. It's an incredibly powerful approach. So it makes you wonder, what other tough problems out there, maybe in science or business or even just in our daily lives, are just sitting there waiting for a simpler, elegant shortcut?